Another example about tilting. So in this example, we've got a non-uniform rod, AB of length 10 meters and weight 40 newtons, suspended from a pair of light cables attached at C and D, where AC is 3 meters and BD equals 2 meters. When a weight of 25 newtons is hung from A, the rod is on the point of rotating, which is really the same as saying it's about to tilt. Find the distance to the centre of mass of the rod from A. So as always, let's start with a nice clear diagram. So we've got the rod's length of 10 meters. So let's draw that out. So we've got A, B, that's the ends of the rods. That's supposed to be 10 meters. It's attached at 2 points. So it says AC, where AC is 3 meters. So that means we're attached at this point C. That gap there is equal to 3 meters. And there's some tension in the string or cable that's holding it up. Let's call that T. We're also told that it's attached at D, where BD is 2 meters. So we've got something here. So some tension there. Let's call it S. And we've also got the weight of the rod itself. So that's 40 newtons. However, we don't know where that is. That's kind of what the question's about, I suppose. So I'm just going to put it here for the sake of argument. And we could call that X meters from A, perhaps. And we've also got a weight of 25 newtons hung at A, which is going to be down here. Okay, so with this question, which I'll work at X overall, the first thing to note is that it's about to rotate. So we have to think about where it's going to rotate about. So if the rod's here, we pull down at A, well, it only makes sense for it to rotate about the point C. Otherwise, if we're trying to rotate about S, then that would mean we were stretching the cable here, which doesn't make any sense. So that means that if it's rotating about C, the reaction at D must be equal to 0. So straight away we deduce that S is 0 newtons. The other thing we can deduce is that if we look at all the vertical forces, we've got T going upwards, and then we've got these two forces that are pulling downwards. Everything's supposed to be in equilibrium because it's only at the point of rotating. So we're going to resolve vertically. So that would mean that T subtract the 40 newtons, subtract the 25 newtons must be equal to 0. And therefore T is equal to 65 newtons. So we're making good progress with this now. The other thing we want to do is take some moments. So I think I might just pick A to take the moments about. We could pick other points, but I'm going to use A, partly because I've labelled this as X, so it's going to make it simpler when we form an equation. So the forces that will actually produce a moment about A would be the 40 newtons, and that's going to be positive because it's pulling it downwards, which would be a clockwise direction. So it's as though we're doing this with the rod. T is going the opposite direction. That would be rotating it anti-clockwise, so I'm going to call that one negative. And then we can just set up an equation from there. So the moment of the 40 Newton force about A, so let's make a note of what I'm actually doing here. So taking moments about A. It's worth writing this sort of thing out because it's making clear to the examiner what you're actually doing. So taking moments about A, saying the 40 Newton force by the positive moment, so that's 40 times by X. The 65 Newton force, the tension in this cable, will have a negative moment, so I'm going to subtract 65 times by 3, and because it's only on the point of rotating, that needs to equal 0. It's still actually in equilibrium. So we get an equation of 40x is equal to 195. So to get what x is, I just need to do 195 divided by 40. And then that comes to 4.875 meters. So in other words, that's the answer to the question. The rod, the centre of mass of the rod rather, is 4.875 meters from A.